Hello, hi guys. It's a new year. I hope everyone is doing very well. 2021 will be taking things little bit different than the last one. So we'll take a different approach. From this year, we'll be doing a series of videos concerning maybe power machine, mathematics, and other subjects. So now we're doing Power Machine N5 from this textbook. So everything that I'll be doing here will be taken from this textbook, right? So what I'm going to do today, we'll be looking at thermodynamics of gas. So we'll be looking at the process, the cycle. Okay, we'll be discussing what is a process, what is a cycle, energy, the heating of gas. So this is E, heating. So the heating and the expansion of gas. Um, all the Boyle's law, Charles law, and the perfect gas, and all those kind of stuff. So this year we'll be doing a series, as I said. So after thermodynamics, we'll be continuing from this textbook, right? So this is you're going to do chapter 1 and going to do the whole textbook, right? So now we'll be looking at thermodynamics, then we're going to heating of gas, entropy, and everything according to this textbook. So I hope by the end of this month, which is January, we'll be done with this textbook, with all the chapters in this textbook. And then I actually recommend if you are doing Power Machine N5 that you use this textbook. This is a good textbook, and I'm not getting paid from this company or from these authors of textbook. I was just making a recommendation, right? So now we'll be looking at process. So okay, before process, we can just discuss what is thermodynamics. So thermodynamics is actually the relationship we look. Okay, thermodynamics of gas, we'll be looking at the relationship between heat, work, and properties of system. Like if we're looking at thermodynamics, we'll be talking more about heat. Also be looking at work. We're talking about work done, or when on heat we're talking about heat energy, and then work we're talking about work done, and also the properties, right? The properties of that system, right? So then now when you're looking at a process, we know what is a process like in general. So a process, we're talking about something that has been or maybe we can say is a substance that has been changed by means of operation. So that's called a process. So that means if you are changing something and you maybe you are operating it, maybe step by step, if you are changing something step by step, we call that a process. And then number two, we're talking about the cycle. So a cycle, we're not actually talking about the cycle, which are the shape, right? So we are talking about, if we're saying a cycle, it's a process that is being carried repeatedly. Yeah? So that means if you are, we said a process is doing something. Yeah? So if we are doing something by means of operating that something, we are doing what? A process. And then a process, that's why you said if we are applying something, there's a process or there's step by step that you need to take to undergo a certain process. And then for a cycle, we are talking about the repeating of the process. So that means if you are changing a gas, if you are changing gas, that means if you are changing the gas repeatedly, yeah, repeatedly, it's a cycle. And then when we're talking about energy, so everyone knows what is energy. But we are here on Power Machine N5, or from N5 we can give a specific definition of energy. Unlike the energy that we define on N2, N3, or at high school. So when we said energy is the ability to do work, it's actually the same. We can then say define it the very same way, or else we can define it according to the textbook. So it's saying energy is defined as the capacity of a substance or a body possessed, which can result into performance of work. So that means if something has energy, that means it has a capacity, or it has a capacity, or it possesses a certain capacity. That capacity can result, right? Can result in performance of work. So that is one, that it's energy. And then on energy, we also have what you called a law of conservation of energy. Now, so the law of conservation of energy. Well, let's write there a conversation. Yeah, conversation of energy. So this law of conservation of energy states that energy cannot be destroyed or okay, energy cannot be created or destroyed. It can only change from one form to another. So that is a common definition. So we have the law of conservation of energy. So the law of conservation of energy by the book states that energy can be a change into many form, but never destroyed. So in such way, we're going to have this formula says energy, heat energy, it's equals to work done plus the internal heat energy. Internal heat energy will be represented by U. So that means now if you are changing, if you are going under the law of conservation of energy, so we can then say the energy that is being changed. So this is your heat energy, or this is the energy supplied, and then this is the work done, and then this is your internal heat energy. So that means if you are going under a certain process or a certain cycle, maybe let's say you are having a container inside, and then there is air inside. Maybe you are compressing this air. Let's say maybe you're compressing in a certain sort of a plunger, let's say, like this, and then you are applying a certain force. Now, so if you're going to apply this certain force in this container, that means you are applying originally there is a heat energy here inside. That's what we call what our internal heat energy is, the energy that is available inside the container, or inside this process, right? When it's undergoing this process. So you have an internal heat energy inside. And then when you are applying this certain force, that means you are applying what you call work done. Remember, work done, we say from engineering science, we can then define as what work done, it's equals to force multiplied by displacement, right? So if you say work done is force multiplied by displacement, that means the force that you're applying on top, right? And then if you apply this force, and then this plunger that you are using, it will go a certain displacement down, right? So if it's go in this length, maybe we can then say it's a stroke length name. So it makes what you call a work done. So that's why you said the heat energy that is inside plus the work that is being done, it's equals to our internal heat, sorry, it's our heat energy, or the heat that is being supplied inside the system, right? So this is the application of the law of conservation of energy. So because already you do have the energy here, but then if you are changing or you are applying a certain force or a certain pressure inside this vacuum, then the heat energy will change. It's either will increase or decrease. But then we said the heat will not, by the law of conservation of energy, we said the energy will not be destroyed. It can only changes from one form to another. So this is heat energy. And then we have also the heating and expansion of gas. When talking about the heating and expansion of gas, we are talking about three things here. So if we are going to concentrate on the Boyle's law, the Charles law, and what you called a perfect gas. Now, so on a perfect gas, so not a perfect gas, let's start with Boyle's law. So the Boyle's law, this one is sometimes called, or is referred to, an isothermal process. So if it's referred to in an isothermal process or an isothermal law, no? So if as an isothermal process, we say a process as the application of something, no? Or it's the change of something by operation, right? By means of operation. So, and then we say the Boyle's law. This law states that at a constant at a constant temperature, the pressure and the volume of a certain mass of gas are inversely proportional to each other. No? So this is actually what you are talking about. So at what at constant what temperature. So we then notice that if we're going at a process of if we're applying a process of Boyle's law, that means the initial temperature will be equals to the final temperature. That's why I say this what is an isothermal. So this then we then said the pressure is the pressure and the volume are inversely proportional. If we're looking here, we have the pressure number one and volume number one. So pressure number one is inversely proportional to pressure to the volume, and then pressure number two is inversely proportional to the volume again. So that means if you are changing, or maybe if you are increasing this one, if you're increasing the first pressure, that means the volume number one will decrease, right? And then this one will increase now if the pressure has been released now. So this is the process of what you call of expansion now. So like now, if you apply a certain pressure, like yeah, sorry, it's a compress it's what you call, okay. So when you are applying let's say let's go back to this example now. So if you are applying a certain pressure now, so when you are applying this force inside this cylinder, that means the pressure inside this cylinder will increase. Then when we're looking at work done, remember we said work done, it's equals to force multiplied by distance. Now, but then now under when we're looking at what you call when we are heating the gas, if we applied this force, we are actually applying what you call a pressure inside. We can then simplify substitute pressure to this force, and then we say the work done is pressure multiplied by, then the work the displacement that is going to move is going to record as what, as the volume. So if this plunger moves, it increases the pressure, it applies the pressure downwards, and the volume changes then, right? So that's why the volume becomes what our displacement. So now when we're talking about work done under thermodynamics, we're talking about the pressure multiplied by volume. So that's give us what you call the Boyle's law. And then when we go to our Child's law, this one states that during the change of state of any gas in which the mass and the pressure, in which the mass and the pressure remain constant. So the volumes vary is proportional to the absolute temperature. So that means the volume number one is directly proportional to the temperature. So on this case, now I will say the pressure is kept constant. That means pressure number one is equals to pressure number two. So this is the state of Child's law. And then when you're moving to the perfect gas, so on a perfect gas, either the volume or pressure in this case is not what is not is not constant. No? So on this case of a perfect gas, we are talking about the combination of both Boyle's law and Child's law. So if we have pressure number one, volume number one equals to temperature number one, this will be equals to let's say pressure number two, volume number two over temperature number two, right? So on this case we call it what a perfect gas, because nothing is constant in this case. So the pressure that is applied in number one is not the same as the pressure that is applied on pressure number two. And then the temperature also are not the same. But then if we're talking about Boyle's law, that means the temperatures are the same. That's why we cancel them here. So if we simplified this formula, we can end up with P1. We can cross multiply. P1 V1 is equals to P2 V2. So this is what this is the law of isothermal. So or is the isothermal process, right? And then this is the combination of these two, right? And then on the perfect gas is where we have what you call a constant, because now if we're going to apply it, if we're going to go another process or another second, so this is a process from 1 to 2, and then we continue to go to 3, maybe into 4. So this is going to be a constant thing. That means you can move from 1, 2, 3, 4 up to the process that you are, or up to the your what you call your suitable final state. So this is what we can then say this P V over T is equals to what you call a constant. So this constant is what is our characteristics of gas. Yeah? So these characteristics of gas is our constant our constant volume. Sorry, our constant is actually this is let's say it's constant. So the constant is actually equals to mr. So it's the mass of the gas multiplied by the characteristics of the gas. So that's where we're going to have the formula that says PV is equals to mRT. So because this T will multiply here we have R. The constant is the mass multiplied by the characteristics of that certain gas. So this is the formula for a perfect gas. So the perfect gas is where you don't have any constant, right? It's where you don't have any constant. And then Let's move to our specific heat capacity. Now, so a specific heat capacity, this is the amount of heat. This amount of heat transfer. Now, this is the amount of heat transfer, or we can say this is the amount of heat transfer, or is from a unit mass of gas, while the temperature changes by 1 degree Celsius, or sorry, 1 degree of what you call, sorry, I'm not saying the right thing. Now, a specific heat capacity. Now, a specific capacity is the amount of heat transfer, or we can say it is the heat energy. Now, transfer required to rise um, 1 unit mass of uh, of a gas by 1 degree, uh, to rise the temperature by 1 degree. So that's why what you call a specific heat capacity is defined, or the units of a specific heat capacity. It's joules, or can say it's kilojoules per kg. So yeah, kg, kelvins or degrees. Let's say degrees. Let's say degrees for now. So by looking at this, we can define the specific capacity. So we can then say the specific heat capacity is the heat transfer. We know that the heat is measured in joules. So the specific capacity is the heat transfer that is required, you know, to rise the mass of the gas, which is what our mass is measured in kg, right? So it's required to raise the mass of the gas um, by what you call, by 1 degree Celsius. Now, so this heat that is needed to heat, like if we wanted to heat water, now let's say we have 20 kg of water. Maybe we can then say it's 20 liter, no? 20 kg of water, or 20 liter. And then you are applying heat. Maybe you are using firewood. No? You're applying heat into this one. So when you're talking about the specific capacity, we're talking about the energy that you will need to rise the temperature of this water by 1 degree Celsius. So that means if this water, maybe initially, yeah, its temperature was 20 degrees Celsius, or maybe let's say 22 because I'm using 20 here. So let's say the initial temperature of this water is 22 degrees Celsius, and then you are heating with the firewood. So the specific heat capacity is the heat energy required to rise this one. So that means if this water can change by 1 degree, that means it's going to change into 23 degrees. So that is your heat energy. The heat energy that this firewood has to provide to change this water by 1 degree Celsius is what you call the specific heat capacity. Now, so that's why when you're looking at the heat energy, when you are heating um, a certain body, it's equals to mass multiplied by the specific heat capacity multiplied by the change in temperature. Now, so because now you know the heat that is required to change this mass by 1 degree Celsius, you can then multiply by this mass and multiply by the change now to get what the whole heat energy that was used to heat this one. So now the change in temperature, you know that change in temperature is temperature numbers, the final temperature minus the initial temperature. Then you will have what the heat energy that was that was given off to the water to change this water into so let's say maybe the final temperature now after heating this one, you say maybe it's 123 now. So if the final temperature is 123, then you know that the specific heat capacity of water is 4.187. I hope I'm correct by this answer, but maybe it is said for the sake of this for the sake of this example. Yeah. So this is the heat energy required to change to change 1 kg of water by 1 degree Celsius. No, by 1 degree Celsius. This one. So now let's take maybe you have a mass of the mass of water is 20. So to calculate the whole heat energy that was supplied into this water so that it changes its temperature to 123, you can then use this formula and then you can say 20 multiplied by 4.187 multiplied by the change in temperature, which is going to be 123 minus 22. Then it gives you the heat energy, right? So this is actually what we're supposed to be talking about here when you're talking about the heat energy at the first time. Okay, but then we have two types of heat capacity. So, okay, we have this specific heat capacity. We have defined it, but then we have these two types of heat capacity. So, if we have CV, this is the specific heat capacity of a constant volume. That's why it has this V name. So, this is the specific heat capacity of a constant volume. It's the same definition, but then now if this heat energy, the heat energy that so this specific heat capacity of a constant volume is the heat energy that is required to change this mass. If we're talking about this water, we can then say the mass of this water by 1 degree Celsius, but then we keep the volume of the water constantly, right? So this is the specific heat capacity of constant if you keep the volume constant. This one is the specific heat capacity of pressure. So that means here you kept the pressure constant. You can define it as what as is the amount of heat transfer to a mass of gas while the temperature it changes by 1 degree Celsius and the pressure remains constant on this case, right? So the last thing that we're going to talk about here is the law of thermodynamics. We only have two laws of thermodynamics, which is the Joule's law and the Cauchy's statement. So the Joule's law states that mechanical energy and heat energy are mutually convected. Now, a Joule's law states that what you call the mechanical energy and heat energy are mutually convected. So this says that they are both of them, they are heat energy. If we're talking about heat and mechanical. So they say these two energy, when we're talking about Joule's law, these two energy are mutually convectible. Mutually convectible. That means if we're going to have heat energy, mechanical heat, okay, let's say mechanical energy will produce heat energy, right? So that means for an example, like if you have a certain, okay, let's talk about the brakes of a car. Now, for an example, to make just simple, if they say it's a mutual convectible. So let's say a brake of a car is made of a brake drum. Let's say this is the brake drum. This is the wheel. Okay, this is where the wheel is mounted. You have a brake drum, the brake caliper here. The brake caliper have what you call brake pads, and then when you apply the brakes, the brick caliber compresses the brick press to hold the brick drum. Now, so this system is mechanical, right? So this mechanical energy, when this brick has been applied, there will be heat that is being generated between the brick pad and the brick drum. So that's why we said the mechanical energy is mutually convertible to heat energy. It's like even if you are rubbing your hands together, if you are rubbing your hands together, the friction between your hands will convert or will produce heat energy. So when you are rubbing your hands, it's a mechanical energy. Then this mechanical energy is convertible into heat energy. That's what the Joule's law states. It states that the mechanical energy and the heat energy are mutually convertible. Um, we know what is mutual. Mutual, that means they are both something that is mutually is something that has two side beneficial, right? And then the cultural statement states that heat can flow from a hot substance to a cold substance unaided, right? But it is impossible for heat to flow from a cold substance to a hot substance without an aid of external work. So this statement says that we know that heat can flow from a hot substance to a cold substance. Like if you have water, now the amount of water here, maybe this water is 2 degrees Celsius, and then you are having maybe a piece of a rod or a piece of a steel that is hot. This steel, maybe let's say this steel is at 120 degrees Celsius. If you're going to take this steel and put it in the water, the heat will be transferred from this hot substance to a cold substance. So until both these substances or these bodies are at the same temperatures. So that's why at the final temperature, um, these two final temperatures has to be the same. Now, the temperature of this water and the temperature of the steel will be the same. That's where heat transfer will no longer take place. But know that heat can flow from hot substance to a cold substance unaided without any um, energy. With if we start saying unaided, that means without adding anything. That means this thing will act naturally.